Hey guys, in this particular video I'll be showing you how to calculate the equations of motion for a pendulum. So let's get started. This is our pendulum right here. This is our pendulum. And this is our unstretchable rope of length L, which always remains L, it's constant. This is our point mass M, and this is our angle theta, which has been defined to be from the vertical to this point just here. And in this particular video, I'm going to show you yet another way you can calculate the equations of motion, which is still using energy methods, but it's a much more complicated way to show it. I'm doing it purely for the sake of showing you that it doesn't matter how you view this problem, as long as you apply the formulas correctly, you're going to get the right answer. So we know that our change in mechanical energy is going to be equal to our work done by non-conservative forces, right? This is a fundamental equation where the work done by non-conservative forces is going to be 0 because the friction force in both the pivot point and air resistance is so negligible we can reject it, and because the normal forces acting here and here don't do any work because they don't actually move the pivot point. Okay, so let's see. What's our change in mechanical energy? It's going to be 0, meaning that our mechanical energy is going to be constant at any point in time, right? And I'll just call that constant K for simplicity, meaning that our kinetic energy plus our potential energy is just going to be equal to a constant 2. Now this is where roads split into different directions. We can choose, based on how we view this problem, our kinetic energy will change, right? The equations we use for kinetic energy will change. So let's see if we can do this. In previous videos, I've said, okay, well, we can view our point mass as just having translational kinetic energy, and we just plugged that in. It was a simple half mv squared, and we did that just fine, and it worked out. Another way we could view this problem, which I did in the second video, was saying, okay, well, maybe this entire system's just rotating around this pivot point, so we can just use rotational kinetic energy then, right? And that's exactly what I did. I used a half I omega squared, and that worked just fine. In this particular video, I'm going to be doing something a lot more complicated, but hopefully you'll still manage to follow me. This will be our mass here, our point mass here. This will be our angle theta right here, right? And if you can imagine it, this will be also our angle theta here, based off our geometry. Right? That'll also be our angle theta, right? And here's the way I'm going to view this problem. Instead of saying that our mass is just having translational motion, or saying we're rotating around our pivot point, instead I'm going to try and view this problem as our center of mass being our center of rotation. Just imagine that for a second. Imagine that our point mass is our center of rotation, and instead of we're rotating around the pivot point, just imagine now that the rope is rotating around our center of mass in a counterclockwise fashion. Just imagine our rope is rotating around our center of mass. So that will give rise to a rotational kinetic energy equation. However, that doesn't perfectly explain the phenomenon we're seeing. Just imagine our mass staying still but the rope going around it. That doesn't perfectly describe what we're viewing. Instead, you also have to include the fact that the center of rotation is moving as well with translational motion of v is equal to r omega, where r in this case is just L, right? So in this very creative way of viewing this problem, we're going to split our kinetic energy into two components: translational kinetic energy of a half mv squared and rotational kinetic energy of a half I omega squared. And we're going to be adding that to our potential energy, which is mgh, and that's going to be equal to our constant that we have here. Okay, so this is where that's the biggest leap we're going to make in this particular problem. Now it becomes a matter of maths, really. Okay, well, what's a half mv squared? Remember, this is our kinetic energy of our center of rotation, right? Which is, in this case, our center of mass. So that's just going to be a half m times v squared, which is just going to be r omega squared, which is L theta dot squared. And that's going to be added to a half times, now what's I? This is a pretty challenging one. What's the moment of inertia around our center of mass, right? What's our moment of inertia around our center of mass? Remember that our moment of inertia is equal to, for a set of discrete masses, that's a pretty funky sum sign, this is the sum of r squared m, right? And in this case, what's the moment of inertia? Well, the moment of inertia for the system rotating around its center of mass, because the rope is massless, each small section making up the rope will have a mass of 0 as well, meaning that 0 plus 0 plus 0, when you add up all of the terms here, will just be equal to 0 as well, meaning that in this particular case, our moment of inertia around our center of mass is 0, right? That's because the mass of each of these small chunks of rope around our center of mass is going to be 0 as well. So that means that our I is going to be 0, and our omega squared is just theta dot squared, right? And now we're adding mgh. What's mgh? Well, we could do what we've done before, but considering this problem's been very different to us so far, let's see if we can view another creative way of calculating h. Instead, I'm going to imagine some arbitrary ground just here, right? And I'm going to put my axis just here. This is going to be y, and this is going to be x, right? And imagine this ball just rotating all the way over here to the point where it gets just there, right? And I wanted to find out h. Remember, h is the vertical distance from the bottom to here. So this distance here is h, right? So that means this distance is just going to be a constant. This distance right here is just going to be a constant, which I'll just call q, right? That's just there. And this distance right here, imagine if the entire ball swoops at a circle, that means this distance here is going to be L. That means this distance here is going to be L, meaning that if you were to create a triangle just here, this distance here would be L cosine theta, meaning that our value of h is just going to be, actually I'll just do it in a separate area. We know that h is going to be equal to, well, what's it going to be? It's going to be q plus L minus this distance just here, q plus L minus L cosine theta. That's going to be our value of h in our particular problem. That's if we choose our coordinate system to be based just here in some arbitrary place down below, right? So let's plug that in. Let's plug that into our equation, and we're left with a half ml squared theta dot squared plus, and remember this term goes to 0 right here, plus 0 plus mg, and what's h in this case? It's going to be some constant q plus L minus L cosine theta, and that's going to be equal to k. Alright, now we've done this a few times in previous videos, but let's just go ahead with it anyway. There's not enough space, so I'm just going to do it down here. I'm going to differentiate both sides with respect to time. So let me write that out. I'm going to differentiate both sides with respect to time, and it's going to be a half ml squared theta dot squared plus mgq plus mg plus mgl minus mgl cosine theta. That's just expanding that bracket just there. And that's going to be equal to ddt of k. Well, ddt, the derivative of any constant, is just going to be 0, right? Whoops. Let's go back to it. The derivative of anything is constant. So that would imply that the left-hand side now is just going to be equal to, well, what's it going to be? The derivative sign is distributive. It has the distributive property, so we can just write that as a half ml squared times ddt of theta dot squared plus, is that right? Yep, that's right. Plus ddt of mgq plus ddt of mgl plus ddt of mg times by minus L cosine theta, and that's going to be equal to 0. I hope that's enough space to write that. Let me see if I can do that. Maybe that's slightly easier. Cool. Okay, well, notice that the derivative of a constant is 0, so these become 0, and this becomes 0, meaning that we're left with a half ml squared times by, and I won't go into the proof of this, but this is just going to be 2 theta dot times by theta double dot plus 0 plus 0 plus, sorry, that should be a minus minus mgl, and by now our math should be fairly good at this, so that'll just be, let's see, the derivative of cosine theta is minus sine theta times by theta dot, and that's going to be equal to 0. Alright, I'm shortcutting this work right here because I've already done this in a few other problems, so hopefully the math shouldn't be too much of an issue, so I'm just going to zoom through this, and that'll be equal to 1/2 ml squared times 2 theta double dot, plus mgl sine theta dot, and that's going to be equal to 0. We can factor out a theta dot like we've done before, and that can be theta dot times by, and remember this half cancels out with this 2, and that's going to be ml squared theta double dot plus mgl sine theta once we factor out a theta dot, and that's going to be equal to 0, leaving us with two solutions. We can say that theta dot is equal to 0. Not a very interesting solution at all, but a solution nonetheless. Another solution we could have is ml squared theta double dot plus mgl sine theta is equal to 0, right? And considering our mass is non-zero and our length L is non-zero, we can divide by both of them, and that's leaving us with L theta dot plus g sine theta is equal to 0, meaning that finally we're left with our solution that theta double dot is equal to minus g on L sine theta. There's our answer, finally. So that was a much more challenging way to view this problem, right? I mean, it's very counterintuitive to view this system as rotating around our center of mass, but you can do it, and I've just proved it. You get the same answer. So that's one way you can do it, and I hope that made some sense to you guys. Cheers.